So people might be late. So let's begin our first seminar of the year of the semester. Our previous one was Sarek that visited us during the winter break. So today we're very excited to have Arthur Wu, who is a graduate student at University of Pittsburgh. He's waiting us for a week together with a postdoc, Kun Cheng from University of Pittsburgh as well, here, who will give a talk on Friday. They both work a lot on different aspects of phenomenology. In particular, they wrote many interesting papers about entanglement observables and colliders, which will be the theme of the talk by Kun Cheng on Friday. And they are here at the FTPI winter office, so feel free to stop by and discuss physics with them. As I said, Arthur was a graduate from USTC undergraduate student who was offered the graduate position here in Pittsburgh. He chose Pittsburgh. I'm not sure if he regret, but we're generous. We invite him back to give a talk. So we don't need to be too soft on him. Let's see his talk on gravitational wave and neutrino.
Okay. Thank you for the introduction. I kind of regret after I see this campus. The campus is very beautiful. I like here pretty much. The physics department is also very good. But that's basically the only one that's significant in our. It's used for classrooms. So Okay, so let me start. So it's a great pleasure to be here. Thanks, Jen, for the invitation. So I'll talk about this gravitational wave and neutrino mass, which is a project I did with our postdoc Arnab and Supriya, and also Professor Tao and Professor Michael. Okay. So in the first slide, I would like to talk about my motivation to look into this gravitational wave study. So as a high energy phenomenologist, I always wonder about this question. So what is the limitation on us human beings in discovering the new physics? So to me, the best way to discover new physics is collider. Collider is the best thing to me. There's no doubt. But as a collider guy, I'm also well aware of the limitation on the collider. So if we look at the next energy frontier, we have FCCHH and muon collider, which all typically go to a paradoxic center mass energy around 10 TeV. And that's it. If we want to go to a even higher energy, we will have to build another and a bigger collider in the far, far future. And even if we have the colliders, the new particle could also be hard to find. And the new particles may be very massive, that is beyond your 10 TeV collider, or the coupling to the standard model are very small, so that you can hardly produce or detect them in your collider. And that motivates us to look into some astrophysics signals, because in the early universe, everything's hot and dense, and the temperature go to as high as 10 to the 15th GeV. And that could potentially produce a lot of these heavy particles, which could leave a fingerprint in today's observations. So in particular, I'm interested in this gravitational wave signal from the phase transition in our universe. So here shows a sensitivity plot of some experiments on the energy versus the frequency of the gravitational wave. And we can do a simple analysis to see that the peak of the gravitational signal should be proportional to the nucleation temperature of your phase transition. And this nucleation temperature is basically at the same scale of the scalar that's involved in the phase transition. And if we do some simple numerics, we will see that if your gravitational wave is here, this corresponds to the peak corresponds to around 100 GeV, and here corresponds to 10 TeV, and here corresponds to 1,000 TeV. So from this simple analysis, we see that this gravitational wave observation would give us access to a very, very massive scalar sector. So as high as this.
Suppose the experiments indeed achieve the design since we so matching this so and then you see some, it says. Is there a way to
tell, oh, this comes from the phase transition, or this is a bunch of unresolved binaries that I keep merging throughout the universe, and I have, for whatever reasons, a set of these.
Yeah, I think to some degree you can do that because the spectrum for the phase transition have a certain a function as the frequency. So if you're able to tell, it's
so you're saying that the power there is a prediction of power as function of frequency.
yeah. So it's not just a simple power.
It's not like a binary.
Oh yeah. Sure.
In your data, right? So
Sure.
this is just a power.
Yeah, but it comes from some like hydrodynamics, like the bubble expansion can predict that.
For whatever reason, the population of binaries that mimics this power.
Okay, then
probably maybe it's this new population, or this is a phase. Just want to make sure.
Yeah.
Even phase transition, they give different slopes.
Sure.
Real source, the driving source of practically.
Yeah, I think if it's a binary and like in some coincidence happen to give you a similar spectrum, you cannot.
One of the backgrounds for Lisa is an unresolved population of binaries.
Yeah, so I think So as long as they're different enough, they have different enough spectrum, they should be able to tell difference.
Power was function of frequency. That's what
Yeah.
So what is T?
What's that?
What is T now?
Oh, sorry, that's the nucleation temperature.
And the nucleation temperature, in principle, it does not need to be correlated with the value location.
Yeah.
Associated.
Yeah, right.
How deep they are.
Yeah, sure. But the order of magnitude should be similar. It's not a simple proportionality. Yeah. Unless you have very, very strange couplings. Yeah.
And here, obviously, you're considering first order phase.
Yeah, that's right. That's right.
So like, you can get a signal from that.
Right. Yeah, that's right. Yeah. So another advantage of this gravitational wave observation is that because gravitational interaction is universal, your new scalar. So even if your new scalar sector has no coupling to standard model at all, that you can never produce it in any collider, you can still possibly see its gravitational effect. So that's why I find this gravitational wave study very interesting. And so in my talk, I'll first talk about how do we calculate this gravitational spectrum. So it turned out that there's a lot of subtlety in the calculation, and so we want to do good phenomenology. We want to be accurate and reliable in our results. That's why we collaborate with Professor Michael Ramsey-Musoff, who taught us about all these advanced techniques to do the calculation. So I'll introduce this simple method versus this more advanced dimensional reduction method in calculating the potential, and also talk about how to cancel the gauge dependence before I go to the gravitational wave spectrum. And in the second part, I'll apply these techniques to this inverse seesaw model to do some phenomenology, and I'll show you how gravitational wave observation would help us to dig out more information that is beyond the collider. Okay, so the whole story starts from the phase transition. So here shows the effective potential of a scalar field, and the blue curve is our familiar Higgs potential at zero temperature, and the red curve is the same potential but evaluated at very high temperature in early universe. Because of the thermal correction, the quadratic term becomes positive, so your wave goes to zero. So what we are interested in is this how this zero wave from non-zero wave, how this transition happens. So one possibility would be the smooth transition there as the temperature decrease, this potential just goes lower and lower, and the wave continuously go from zero to some non-zero volume. And the more interesting case would be this first order phase transition, where there is a barrier between the two minima. There's a barrier between these two minimums, so that above this critical temperature, the true wave of the universe is zero, and below the critical temperature, the true wave suddenly goes from zero to this non-zero volume. And this sudden change of wave would create some bubbles of non-zero wave out from the zero wave universe, and those bubbles will expand and collide with each other. That's how you generate the gravitational wave. So from this picture, you can see that you calculate the gravitational spectrum. Everything starts from this effective potential. So to be able to make reliable prediction, we want to be able to calculate this very accurately. So now let me briefly talk about how we do the calculation. So to calculate this, we need to know some basic facts about quantum field theory at finite temperature. So it turned out that the thermal field theory is very simple. So the only difference is that the time direction now becomes periodic with an imaginary period of inverse temperature beta. And then you can derive all the other features from this simple relation. So first, if you do a Fourier transformation of this periodic time direction, you will end up with infinite number of discrete energy mode proportional to pi t, which are called the Matsubara mode. And this is the energy mode that goes into the denominator of this propagator and this exponential time. And you need to sum over all these energy modes. And similarly, in the looping book, you need to not only integrate over the string momentum, but also sum over all these Matsubara modes. So that's all we need to know for the thermal field theory. So now let me briefly introduce this simple method to calculate the effective potential. So in the simple method, you have this zero temperature correction plus and high zero temperature term plus and high temperature corrections. So this the tree level term is just a Higgs potential, and this one loop term is given by the Kolmai-Weinberg potential, which comes from evaluating and summing all these one loop diagram with scalar external x. So the first,
So, in what sense are you signing the diagrams with different number of external legs?
Like you just sum basically the endpoint function, right? You sum from 0 to infinity, and that can be becomes a log if you do that happens to be for a serial expansion of this log term.
Okay, in the background though.
Yeah, that's right. It goes external lag. Yeah, if you draw field.
Is it necessary that this is an important contribution
or? In many cases, well, I would say like 10% correction to your tree level results.
and is the rest of the calculation going to be good to 10%?
No, I'll mention what's the problem of this later. As for the zero temperature part, there's no serious problem. The high temperature contribution are the problem.
Well, that I can understand is important because that's your phase transition.
Yeah,
But I'm
yeah.
just wondering why the zero temperature one loop
Oh.
potential.
Oh, yeah, we just want to include them anyway. Yeah, we just want to include them anyway. It's like easy to calculate. So yeah.
But where's your barrier going to come from? This term or the?
Oh, the
one-
temperature dependent term.
The
Yeah.
one temperature. The
Yeah,
temperature.
yeah,
So
exactly.
you're gonna use the temperature.
Has to be a non-analytic Higgs, sort of five.
Yeah. That's right. The cubic term can be the yeah. So
So the and some ends, you have multi-standard.
oh yeah, that's right. So and they could be even like gauge fields or fermions, and fields and comes the very freedom for that, but they can write in a more compact way in terms of some effective masses.
So you don't necessarily assume a barrier at zero temperature.
No, it comes from your model.
No, but the barrier persists at zero temperature, right? But that's what I'm asking, yeah.
Oh,
Do you have a barrier at zero temperature? or not?
We only need a barrier at high temperature.
But at very high
it can be
temperature, you don't
zero
have a
at
barrier at all, but yeah, I mean.
Yeah,
you
sure.
figure
That
it's
intermediate temperature.
No, the temperature becomes zero, there is no pump, there's no barrier.
Yeah, but there could have been a hump. There could be a hump.
Yeah, it could be. Yeah, it could be.
Yeah, it depends on your model.
Yeah.
Are you gonna
right.
engineer a model to have a hump at zero temperature
Yeah,
or
yeah.
not?
Yeah, it's not necessary, but we can do that. Yeah.
In your model, you are relying on the finite temperature.
Yeah.
So in your neutrino model, eventually, when you get to it, you're just gonna rely on the
The-
hump coming from temperature.
Yeah, that's right. Yeah. So so this next correction comes from exactly the same diagram, but you evaluate them using the thermal field theory and do it in the high temperature limit. So that's the first piece.
And you're going to include this, or you're going to talk about it?
Yeah. And the last term, the basic term accounts for the thermal correction to the mass here. And that can be evaluated from this one loop diagram using thermal field theory.
So now what is the pieces question back? Which term is more important for your side?
Yeah, okay. This basic correction typically give you a cubic dependence on the phi, so that could generate a barrier. But this the first piece, this can also change your profile up and down a lot. So I'll say they both contribute. They're both important.
Well, in some sense, the one loop zero temperature correction and Daisy, they are all both a one loop.
Yeah, that's right.
There are some certain cancellation needed in their form, but certain residual part. You cannot. I think you cannot discuss piece by piece unambiguously.
I think so indeed there's another way to include this mass correction is to directly put this here. And this term basically comes from you expand this term and then you have this. So it is indeed correlated. But if you want to expand this in another term to separate out for discussion, as people sometimes do. Yeah. Okay, so that's all for the simple method. So, and as you can see, it's not very accurate. It contains some correction to this, some correction to that, and it's not systematic. So indeed, there's some problem with this simple method. So the first problem is that there's some there's low accuracy in this method. So people find that there's O1 uncertainty for some of the quantities near the point of phase transition, and that basically comes from the height of your barrier, because your barrier is generated from your one loop diagram. And at the phase transition, this one loop contribution could be comparable to the tree level contribution. And so the second problem is that there's uncancelled scale dependence in this method. So your effective potential typically consists of these two terms, these two logs. The one is associated with your effective mass, and the other one is associated with your mass of balance scale. And these two terms doesn't cancel with each other. And to make things worse, typically we have this effective mass much smaller than this Masubala scale. So you cannot choose a single mu so that you minimize these two log terms at the same time. You always end up with a large log that will spoil your loop expansion. And the third problem is that there's no systematic thermal resummation included in this method. For example, the Daisy term only accounts for the thermal correction to the mass, but there's no thermal screening effects on the couplings. So that's why, so these problems are not just some simple problem, it will cause some real issue in practice. So it turned out that if you proceed with this simple method, you would typically end up with a few orders of magnitude uncertainty in your gravitational spectrum. And sometimes you can't be even certain whether or not there is a first order phase transition. Okay, so that's why we want to use this more advanced dimensional reduction method.
There's still a need for good reason for why things doesn't work, right? So your expansion parameter is pi t. Pi t is much bigger than any other scale in the system. So
that's right.
High temperature expansion seems to be a reasonable thing to do.
Yeah.
So
yeah.
you go back, if so the weight t part should be fine, right? So
Yeah,
you're
that's right.
talking about the next thing. Next thing are the residual logarithmic dependencies, which seem to be, there's only one big number, right? That big number in your system is log pi t squared.
Yeah, that's right.
So if I said mu squared equal pi t squared, all my remaining is m squared over pi squared. Right?
Yeah, but this.
That's too large.
Yeah.
But m squared should have been evaluated because I concerned about the phase transition barrier, right? So at the phi non-zero, it's still a big value. m squared is a big number. Generically of the size of temperature.
Yeah.
So that log is not
Yeah, right,
T
but
over T.
yeah, but not as large as pi p. That's
Yeah, so there's just a pi, log of pi squared.
no. I mean, this like consider this to be like 10 times smaller than that. That's log 10 squared.
Yeah, pi.
Yeah.
Doesn't seem to be too big of that.
Okay, so yeah, another reason why this is a problem, so that because near the phase transition, right, your barrier is generated from your one loop term, right? Your it's a radiated generated barrier. Your scale uncertainty is also one loop, so it's as high as your barrier.
Yeah, I have order one.
Yeah. So that's a problem, right? You don't want such a big scale dependence.
But you don't need to have the barrier generated by one loop, right?
Yeah, if you consider tree level, yeah, that's right. Yeah, if it's tree level, then you have less problem. Yeah. So actually, in our model, it's a tree level generated, but if we calculate the one loop and the two loop term, they also, contribute. Yeah. So.
So you in the end, you put a tree level barrier in
Tree level dominant, right?
Yeah. Okay. So sorry, maybe I shouldn't say tree level. So it's not there at 0 temperature. Yeah. But
not there.
Yeah. But
But in a VT term, not in daisy or not in one loop.
VT is also one loop, right?
VT wouldn't generate a barrier.
VT is also one loop, right? VT is also one loop. Okay.
It means VT one loop.
Yeah.
Yeah, but that shouldn't generate. It wouldn't generate a barrier.
Yeah, I'll say it's still thermal. Yeah. I'll say it is still thermal. Yeah. When I say the tree level, I just means this term. I just mean I included this term, but sometimes. Like two scalar fields.
Two scalar fields.
Yeah. You have two scalar fields, and then
one of them fixed, please.
Yeah. Oh, okay. I'll show this in the second part. Yeah.
Okay,
Then this will make sense. Yeah. Okay. Okay. Let me go on to this dimension reduction. So the basic idea of this dimensional reduction is very simple. Since these Matsuburg scales are so heavy, we can just integrate them out as we integrate out in the effective field theory. So the reason why this is called the dimensional reduction is because we start with a 4-dimensional theory with a periodic time direction, and after we integrate out these Matsuburg modes, we are end up with a 3-dimensional theory with trivial time dependence. So it's actually an effective field theory calculation, but you happen to reduce one dimension. And in response to the previous 3 problems of the simple method, here I show the 3 advantages of this dimensional reduction. So first is you can easily go to a 2-loop accuracy because your 3-dimensional theory is super renormalizable. So the 2-loop calculation would be simple. So I actually calculated this 2-loop term by myself by hand. So the second advantage is that the scale dependence also cancels to a high accuracy, and there are no large logs remaining. And it's also easy to understand because now you do the EFT calculation. When you calculate the thermal loops, we assign a hard scale to this log. And then there's this effective theory and calculate these scalar loops, we assign another scale to this term. So now you have 2 different tricycle scales, and you're able to minimize these 2 terms at the same time. So, and the third advantage is that in this method, there's automatically includes the thermal resummation on both the mass and the couplets.
But sorry, this calculation, when you split it into 2 effective field theories, was this is your calculation, new calculation, right?
Yeah.
Because it was done previously. People.
Yeah. Sure. This is not new, right?
Yeah,
this is not new.
It's 2 different mass scales,
Yeah.
hierarchical. You had it as well.
Exactly. That's
Integrate out
exactly the
first
truth.
mass, and then
Yeah.
get the theory for the second mass. And
That's right.
Yeah, so it's what you're describing is very similar to these papers of Manahan. It's
Some very standard effective field theory treatment.
But in the end, you still have a finite temperature result, right? So
Yeah, yeah.
your finite temperature dependence is coming from
These effective parameters.
integrating out.
That's
The
right.
rest is zero, seeming like zero temperature calculation. I still have
I'll show you.
Between
I'll show you the approach in the next few slides. So I'll actually show you how to do the so before we do that, we need to be familiar with the scales we are working with. So the heavy scale is the Maxwell scale, height. And the second heavy scale comes from the thermal correction to the longitudinal gauge force. That's a mass of the gauge coupling times the temperature. And the mass of the sphere field near the point of phase transition is typically order of magnitude smaller than that. So so we first integrate out this heavy Matsuburg mode. We have some purely linear rotation factor and some matching conditions, and then we can write down this three-dimensional effective coupling in terms of these four-dimensional loops, thermal loops. And in the loop integral, we sum over all these non-zero and the heavy Matsuburg scales. And then in the second step, you can choose whether or not you want to integrate the longitudinal gauge function depending on the scale hierarchy, which is just some standard calculation. So now you are able to write down this three-dimensional effective parameter in terms of these original four-dimensional parameters. And here shows an example of the tree and the one loop and the two loop contributions. So next, you also want to include the RG running of all your four-dimensional parameters to improve the convergence. And now we can write down this effective potential in terms of these effective couplings. And here shows you the result, the tree, one loop, and the two loop. So then we just plug in this effective coupling we just obtained into this result, and that completes our calculation of the effective potential in this dimensional reduction method. So
let me ask again, in your first step, we will integrate out the n-pi-t modes. Right?
That's right.
You will get the 3D potential that is a function of t, although
no longer
t as the active degree.
Well, you can say you get the potential, or you just get the model effective parameters in your 3D Lagrangian, right?
Next slide. What's the effective potentials dependent on heat?
Just get temperature.
This doesn't depend on temperature, but all these parameters depend on temperature.
So you embed the temperature dependence into the
effective
3D parameters. Lagrangian term.
That's right. So that's.
And your effective potential is still using formula number, or is it something else? Or you do
this one loop piece is basically the comma number.
Two loop you calculate.
Two loop is just like that.
So one loop, why do I need to go on? I should just do my loop calculation as I did my two loop time.
Sure, you can. It's the same, right? Like if you do this in the expand in the background field and expand into endpoint functions and sum over together, that's the Kolmai bundle approach. Or you can just calculate like these vacuum bubbles. Right? But the result is the same.
So since you get two loop effective potential, why don't you just include two loop argument? Why do you include?
There's a power content in this. So to get to like gauge coupling to the force accuracy, that's all you need. If you do a power content of the coupling.
So the two loop effective potential also is up to g to the force, help you to finish the g to the force.
Yeah. So as you can see, this method is a bit complicated, but it is worth it, as I will now show you a comparison. So here shows the effective potential of the traditional method in dotted line versus the dimensional reduction method in solid line. And as you can see, they qualitatively agree with each other. However, if we look at the scale dependence, you will see that this traditional method suffers from this huge scale dependence in transition. well, this dimensional reduction method is what it's also one where we see that.
Here, how do you evaluate scale difference? You vary the RG scale
Yeah.
of the
Yeah,
your
yeah,
calculated
yeah, that's right. And in your sorry, it's a bit small, but there's some mirrors.
There's some mirrors for
Yeah.
Oh, so ideally, it's really unlocked RG scale.
Yeah, that's right. If you go to infinite loop, yeah, yeah. Okay, so yeah.
to explain why you go to the evaluation, why converge is so much better. You secretly did some resummation.
No. Well, so there is some formal proof that this is effect. So this is not surprising. Right. This is basically an effective field theory calculation. You integrate out the heavy degree freedom and do the consistent loop calculation in the high energy, and then you get the effective parameter to do in the low energy. So
you integrated out the Matsubara frequency.
Yeah.
That's what you did. You integrated out that
Yeah.
Matsubara frequency, so it takes out that part.
Yeah,
It just leaves you with one scale in the low energy theory,
Yeah,
which is
yeah.
n squared phi.
yeah, and
That's what happened, because the pi t squared came with its mu, n squared came with its mu. If you integrate out the pi t Matsubara frequencies, you're only left with one log in low energy instead of the two.
yeah. So you
So
can
that become insistent to that.
Well, then now you just have one log, one scale, and then now you can
so you can
choose
yeah,
you now.
and you can actually show that your RG running of your coupling cancels with the scale dependence in your effective potential.
That's also known as
Yeah.
patterns of that.
Yeah. That's right. Yeah.
Yes, but Colin Szymanski, whatever, that in principle, I can apply that to my traditional method. I also get.
Oh, yeah, but if you have
large
one
as
log,
well.
yeah, if you have one log, you can do it, but the problem
Yeah,
in his
yeah.
calculation, he had two logs,
Yeah.
but and hierarchically different parameters. So you had n squared phi and pi t squared. There was a big hierarchy in those two parameters. And you can't use one u to
minimize both.
minimize both
Yeah.
logs.
Yeah.
So you integrate out the pi t, which is some Matsubara temperature dependent mass, and then you're just left with one log at low energies, with one scale one. This is assuming your scale is much below. Yeah, but.
Yeah. That's typically.
Much below that.
Yeah, that's right. So the temperature is always much higher than the scale we are considering. So it's unless it's super cool, it's then the temperature become low, but that's not the case for our model.
Just curious, in my traditional method, can't I introduce two scales, the servo scale versus vacuum scale?
Yeah.
Solve the set of equation, minimize them both, and
Yeah.
that is.
Oh, we want to use one u to minimize both.
I think
I don't want 1 mu, I need 2 mu, because
Oh.
there's two scales in my system.
yeah.
There's a dynamical scale, the side of acceptation,
Yeah,
and
yeah.
that is controlled by the thermal temperature. There's a static scale, that is the field
Yeah.
dispersion. So
Yeah.
these two are, in principle, two separate scales.
Yeah, that's right. Yeah.
I could, I hard on that traditional method.
I think you will eventually go to this EFT approach. Yeah, if you try that. Yeah. Okay. So okay. So that's why we choose to use this dimensional reduction method. It's more reliable because it cancels scale dependence, and it's more accurate because it can go to two loop. Okay, so that's all I want to say about this method. And the next subtlety is the gauge dependence. So if you have a look again of this effective potential near the critical temperature, so this effective potential we obtained is by definition gauge dependent, and this is not surprising because it is not an observable. However, people find that if we do this so-called H-bar expansion to expand this effective potential in terms of this tree level one loop to two loop term, and also this this phi that to minimize this potential as tree and one loop term, and then expand everything around this tree level minimum and apply some corrections. And then this minimum of the potential as a function of the temperature becomes gauge independent. So that's how we calculate the critical temperature. As for this nucleation temperature, we need to calculate this effective action, and not surprising, it's also gauge dependent. So the basic idea is similar. So people find that if we do the so-called derivative expansion to expand this effective potential and this field with normalization factor into this leading order and next to leading order piece, and write down this effective potential in this leading order next to leading order, and then we minimize this leading order effective potential to effective action to get this field for some phi and put it into the next leading order effective action to integrate. So the basic idea is also to expand near the leading order term. So now this result also becomes gauge independent. So that's for the gauge dependent. Okay, so now we are ready to calculate all these parameters that we need to find the gravitational spectrum. So the first one is the nucleation rate is basically the exponential of the effective action we just calculated. And the nucleation temperature is given by the temperature when this ratio equals to 1, which means there's 1 bubble per Hubble radius. And we can also calculate this vacuum energy density and this inverse time scale, and this also bubble velocity in terms of the effective potential and the effective action that we just evaluated. And that's how the parameter we need to find the gravitational wave spectrum. So the spectrum typically contains 3 parts: the gravitational bubble walls, the sound wave, and the turbulence. And for each of these, people have done model-independent simulations to find out this parametric form in terms of these parameters we just calculated. So they are typically written as the magnitude times the shape fraction. So for the question at the beginning, I think if you are able to fit these shapes, well, you're able to tell that comes from these sources. This is a function in your frequency, so complementary shape is doing that as well.
Yeah, if you start with by a particular source, the peak will make the shape have a particular slope, so that you can identify.
Yeah.
The mixture you will have more.
Oh yeah, sure.
And also you have a certain maybe.
Yeah. In the ideal case. Yeah.
Sorry, what did you assume about bubble wall velocity? Go back one slide.
Oh, yeah. So here is some simple estimation. But we actually use the package called WALGO. It was, I think, released recently to calculate this from first principle. Yeah. Yes. It seems to be consistent. Yeah. So what we need to do is just to calculate this parameter and plug in into this parametric form. That's how we find the spectrum. So now I would like to summarize a bit for the first part. So we learned to calculate this effective potential using this dimensional reduction method to cancel the scale dependence. And from this effective potential, we can calculate some parameters, and we need to be careful. For gauge dependence, we use this H-bar expansion and the relative expansion. And finally, we put these parameters into the multi-dependent simulation to find the gravitational spectrum. Okay, so that's all for the first part. So in the second part, I will apply this to this inverse seesaw model. So first, let me briefly introduce this model, although you must all be familiar with the seesaw model. So to solve the problem of the neutrino mass, we can use Higgs mechanism and include another right-hand neutrino. And after symmetry breaking, this will give you a mass term. But the problem is that the cutoff must be extremely small, which is unnatural. For this reverse seesaw mechanism, we can include another stereo neutrino with a Dirac master and a non-random master, so that you have this 3x3 mass matrix. And after you diagonalize this matrix, you find that the neutrino mass is naturally suppressed as long as your mass scale n is large and this mu scale is small. So in our model, we adopt the same idea. The only difference is that we choose to generate these 2 scales and then mu from the graph of 2 scales with sigma phi. So the sigma, which has a very large rank, and we give you this heavy scale. And phi, which has a very small rank, light scale. And now we can write down the neutrino mass internal these Mikavas and this web of phi and sigma and h. So and here shows our particle content. We have 3 generations of right-hand neutrino and 4 stereo neutrino, and also 2 spiritual sigma phi. And we assign them some U1 charge as well. So yeah.
Is it a unique UV completion or there are the trust?
Oh, this is like the seesaw model itself is like UV complete, and we just include another 2 scalar field to generate the mass. Yeah, so it is if it's unique, I think there are a lot of ways to make a UV completion model based on your seesaw. So yeah, this seems to be one of the most simple ways we can think of. Oh, because later when we write down this scalar potentials and also this Mikava interactions that help us to use a gauge symmetry to write down all the possible terms. Yeah.
So you don't need the gauge symmetry.
Yeah, I don't know. Yeah, that's right. But
you're not using gauge boson at all.
yeah, but we it still comes in the effective potential, although it's just a loop question, but we include this at this anyway. So it's yeah, I'll say it's not very necessary. Yeah. I just yeah. Yeah, that's right.
But you said that you tried to explain a naturally small parameter.
Yeah, that's right. So
but with all these scalars, there's quantum correction.
what do you mean the quantum?
You have a hierarchy problem.
Oh, okay, yeah.
Scalars, so
Okay, yeah.
you
Yeah,
don't
sure.
really
That's
remove any unnatural. You need tuning.
yeah, but this becomes this scale squared. And this can be small, this can be small.
But the mass of S is dependent on the current, which is what I'm finding.
Oh, okay. Yeah, that's another different problem. Yeah.
Cool.
I hope I can solve that problem.
Oh,
Yeah. Sorry. Yeah, it's a formula.
Can you say what the scales are? What we're talking about? What's the size of the bevs and what's the size?
I'll show you in a much later part in the model parameters. Yeah, it's basically so the sigma is 10 or a few TeV and this the phi out is
Phi has a tiny bev.
yeah.
Oh.
No. Yes.
Yeah, sounds dangerous.
So mu phi is of order of GV. Your parameter mu phi.
Oh no, it's actually very large. So the mass of this phi is there, and also T that just a web is very small. And this is because of the trilinear term, as I will show you. Yeah. I'll show you. Yeah. Okay, so I'll show you the next slide. So let me first finish this Mikava.
Your lepton number is broken by the new parameter explicit. This y phi and y phi bar, they're breaking. Are they exclusively breaking the lepton number? Mu breaks lepton, right? Or that's how the
Yeah, right, that's right. Yeah.
And y phi break is it exclusive break?
Yeah,
Phi gets a web.
After it gets a web.
Sign lepton numbers, they're always particles.
Yeah.
Does Wi-Fi is symmetric or not?
Yeah,
I would say no.
The match.
I think it just satisfies the symmetry. I mean, y sigma, is that right? Sigma and base. And you
So at the end of the day,
Phi gets a web and break the.
okay, then these terms break this number explicitly, right?
Yeah.
Because
Yeah.
that's why simple question.
I don't know, phi SS, doesn't that preserve? What are the lepton numbers of the field? Isn't it this U1D is the?
We always spend a small.
No, it's not the lepton.
Yeah,
Because the L and Y is zero. So then So then what does,
You always get
phi
a,
carry lepton number?
I mean, you always get a small broken of the lepton number if you have a very random term, I think. It's,
Well, yes, well, but you need this mu to be empty, right?
Yeah.
Which is,
What is the value?
I suppose
Mu is Wi-Fi times the
if
derivative.
you,
that's already an effect in the description. The question is whether, you know, if I put phi vacuum expectation value to zero, do I still have a left-hand number?
I think then you don't.
Because at the level of the left hand.
Yeah, you has it, because.
I think that is
It's the only one that carries lepton.
So, but you can
Phi is
assign,
no lepton. Phi has lepton.
but you can assign that number.
Yeah.
You can
If you
assign it,
assign,
you did.
yeah, number two. Oh, yeah, I did that.
Exclusive variant.
But that-
I would say it's exclusive.
But did you assign phi? Does
No,
lepton
no,
number
no,
or
no,
numbers of
no.
freedom? He didn't assign phi lepton number.
Well, then it's gonna, well, if S has
Yeah, but-
lepton.
But phi doesn't couple to any fermions anyway, so.
Why does it, it's the third.
I mean, if you, the charge assignment is following.
I
the
don't
same-
think that's lepton.
Yeah, if you give a neutrino, right-hand neutrino or lepton, then
Yeah.
to claim sigma has the lepton number, then S have a corresponding lepton number. It's
Mm.
Sigma should have the opposite lepton number as 2R.
Yeah, then
Right.
S doesn't have.
And then phi and S don't have to have.
Yeah,
lepton.
you can do that.
Exactly.
Yeah.
Because it's not,
But then
But I'd say it's
sigma,
explicit. Sigma.
sigma will break lepton, won't get you that.
yeah, but then it's spontaneous, it's
Yeah.
not explicit.
I mean, in both cases, I think it's either broken by sigma level, by that, you have that choice in assigning that. But we
Right.
didn't assign explicitly.
But you didn't assign anything, so we can't tell.
I see.
Either-
Would that cause any?
Probably spontaneous.
Yeah, it's both spontaneous.
Yeah, but then if it's spontaneous, there's a Meyer.
So would that be cause any of the?
So they call it this, they should have called sigma, but it's okay, it's fine.
Okay. Okay. So
It's okay, it's explicit.
okay. Yeah. I would like to talk about it later. I have a question actually. Yeah. Okay. Let me proceed to the color sector. So so after the central breaking, we will have this 10 by 10 mass matrix for this block matrices. We assign some simple almost diagonal Yukawas as example for the illustration, and of course we'll include also this neutrino mixing matrix. Yeah, so for the scalar sector, we have some normal scalar interactions. We have some partial and quadratic term of single phi, and also include a linear term. Phi. We also turn out a small mixing for Higgs. So, and it requires the profile of the effective potential to look like this, so that the VEV, the VEV of the universe goes to a very large volume for sigma, as required by the inverse seesaw. And if you zoom in that point, you see that because of this trilinear term is phi, because it's a very small value. So that will give you the suppressant.
So what are the units? TV or?
No, I think it's a random unit. So
I think you normalize everything towards the mu phi square. There's only two scales in your problem.
Yeah.
Show that mu phi.
Yeah,
It's
yeah, so the-
because if there is no, like if it's spontaneous, will be at least 5 to minus 5 symmetry, right?
Yeah, well, he has, he only plotted the one quadrant there.
Okay. Then there should be domains.
Yeah, there are
Different,
domains for-
five values.
Yeah.
You want to.
This potential is fixed by the U1D then.
So Myron is different by something or
Oh,
by the?
no, there's
Well,
no gauge both. There's no gauge both. Wide scale shifts it.
And you decide to gauge your 1D, so
You didn't
there's
gauge
actually.
what these.
There's not good.
Oh, yeah, we gauge this.
Oh, you did
They
gauge.
gauge,
it.
but
Oh,
that's
then-
not the narrow direction. If there's a small misalignment, I think.
Yeah.
But
What's
what's,
not clear to us?
yeah. But what's the role by mu tilde term?
Oh, it's to generate this.
To tune the web location.
Yeah. Basically,
Phi to be extremely small.
Yeah,
right?
so this is
The linear
proportional.
tuning of phi location.
it's proportional to this.
Is a tuning.
Yeah.
So again, what's the size of these?
Oh, yeah. Oh, so actually, this is 0.1 G.
0.1 GeV.
Yeah, Tong G.
And that means but the mass of phi is what?
The mass of phi basically like the curvature here. It's still dominated by this quadratic term. Yeah, so it's yeah. I'll show you. I actually have the number. Yeah, it's
Yeah.
yeah,
Or had other source of mass.
So. It must, so it must be very steep. Potential, right?
The tuning location.
Right.
Yeah, so there's normally a quadratic one, right? The mass and the web is correlated by the lambda, but he had a linear tilt.
Yeah.
Tilt to shift the minimum.
Yeah,
without shifting the double derivative.
Yeah.
So this is, you're doing this tuning to build a signal, right?
To build the neutrino mass.
No, to build the gravitational wave signal.
No, that small mu tilde term is not very important.
But your phase transition, what temperature is it gonna be at?
Also around TeV.
Yeah. I'm saying you're choosing the parameters to get the phase transition at a TeV, get a gravity wave signal.
Yeah, sure. Yeah, of course you need to choose some.
And the masses of the S?
The mass of
The fermions, yes.
the fermion, it's also a few TeV.
Size of the web.
Yeah.
No, but one of the webs is tiny, right?
So when everything is in
Speak
TeV and there are no light particles around, that sounds like exclusively, it doesn't sound like a spontaneous. So,
So it's driven by the webs of these two fields. You can integrate them out.
okay, then there is an ambiguity in terms of what I energetically can understand these things. Because I know that, if I sample enough space, right, and I have different domains, different arbitrary webs, then there should be a restoration of right?
It should be one more massive, right?
Yeah.
Oh,
Are you sure there is no Myron or anything like that? Like very light certain number goes and boson?
I need to check that. Yeah, I need to check.
I see. I mean, phi is a complex field.
Yeah.
It has, there's a ghost mode. in phi. That's why they want to.
Isn't there another fermion rule?
Yeah, that's right. But it doesn't have this mixing to this neutrinos. So I didn't use them here. Oh, it's actually there's a lighter one, but it doesn't mix. So it's true stereo. No, I think a few GeV after I diagonalize the mass matrix.
Since you have a light web, I mean, why isn't there something in the mass of order to web?
It's a massive difference between the heavy mode and all of the time. So they all have a heavy Dirac mass. By the
Yeah.
The web generally splitting to the Dirac mass.
Yeah, I think it's the mass are mainly outcome from this pattern.
Yeah. So 5 TeV is the big M, right? Capital
Yeah,
M is the 5
yeah.
TeV. You generate the splitting.
Yeah. Okay, okay, so
It's a diamond around a mass is split, otherwise the other thing. Yeah, that's right.
yeah, that's right, that's right.
It gives us time,
That's right, that's right.
Wi-Fi, right? Is Wi-Fi
Yeah.
times
Wi-Fi,
yeah.
Yeah, but the question is whether there is whether this Lagrange breaks it explicitly or it breaks it spontaneously. Because it breaks spontaneously, lepton number, that should be a nine.
Yeah, but I think he can do it explicit.
Okay.
Yeah, it seems that.
But so mu is small.
Yeah.
Small.
Yeah, yeah.
Small
Yeah, yeah.
number calculation.
Yeah.
So mu have two effects, right? Generate small mass splitting between all the Dirac mass terms, and also have three lattice mode we identify as neutrino that is proportional to
Yeah, that's right, that's right.
by DO and theta.
Yeah, that's right, that's right.
Well,
Yeah. Okay,
so
so
there are like the lattice mode is neutrino.
yeah, so that's basically all of our new interactions, and since this is a neutrino model, we need to satisfy some constraints. So the first constraint is, of course, the neutrino mass. We have the kinetic mass and the total mass bounded by 0.1 and 0.8 electron volt. And the second bound comes from the non-unitarity of the neutrino mixing matrix, because the neutrino mixes the stereo neutrinos, the mixing between neutrinos themselves are a non-unitary term, and this will also subject to some strong constraints. And the third constraint comes from the mixing to have a neutral lepton, and this can be bounded from the collider, for example, and I'll see this production can here shows a current bound. So it's typically around 10 to minus 1, about 1 TeV. So and the first one, the most important one in neutrino is the beta decay. The constraints on this effective mass, which is dependent on both the mixing between neutrinos themselves and the mixing to the neutral lepton, and it's bounded by around 0.2 electron volt. So that's how the bounds we considered for our model parameters. We always make sure we satisfy these current constraints. Now let's talk about some signals. So the first one is a gravitational wave. So with this scalar potential of two scalars, we are interested in this two-step phase transition where so at the high temperature, everything is at the origin. At an intermediate temperature, this phi gets a value, and as the temperature decreases, the value of phi restores, and sigma now gets a value. So, and in the second step, we require this to be a strong first order phase transition, which give you the gravitational wave.
And so first phi gets a big value.
Yeah. This is also like TeV level. Yeah.
And then then there's a second transition.
Yeah, a second transition.
And phi goes back towards the origin.
Yeah, towards 0, but it's a very small.
Right.
Yeah. So here shows the effective potential in this 2D points in that phi. So it's more blue is more negative, the minimum. So as you can see, everything is here at high temperature, and the temperature decreases phi, that's the minimum. Temperature further decrease, this sigma develops the minimum. And as you can also see, there's a barrier between the minimum and this transition begins. Okay, so now we can also get some feeling on the phase space of these parameters. So here, the iteration I fixed this to mu to be 2000 below 4400, and here shows phase space in this lambda sigma and lambda phi. So basically, this green region gives our desired two-step switch transition, and here is one step. So next we would like to project on this, allow this solid green line for these two and see what's the dependence on the other lambda phi time.
Just to make sure, in all those phase transition discussion, you did your dimension reduction. Right?
Yeah, with all these two loop calculations.
And you actually follow the transition through the formation of the bubble formation and completion of the transition?
No, I didn't do the hydrodynamic part. I just
because you said there's still another minimum
Yeah.
large phi.
Yeah, yeah.
How do you know you actually,
Complete.
yeah, how do you?
Yeah, I just, you mean complete the
How do
feature
you know you don't
actually.
get stuck in the false path
Yeah, so
from the other?
I do check that. And so in certain region in the first order field transmission, it is lambda sigma 5. And so this term actually the new tree level barrier. So when the tree level barrier is too large, this transition cannot complete and it gets stuck. Right, so yeah, I didn't plot this explicitly here, but it should be like about a certain line, so you will get that. Yeah, but I checked that. I will do that.
I'm sorry, but so you're saying below some line there, there's no longer a barrier?
Yeah, like here, there's no barrier then.
It's the second line.
Can you go back one slide?
Yeah.
So here you said there is a barrier between the two.
Yeah, that's an illustration.
So there are other parameter choices where there's no barrier between?
Yeah.
And
Yeah,
the height
that's
of
right.
barrier is adjustable by the size of lambda sigma 5.
Yeah, that's right.
So that's why you can map that.
Yeah.
But that's a tree level adjustment.
Yeah, a tree level
That's something
adjustment.
people Concentrating on the fact that it comes in common blind, but at the end of the day, you adjust the tree level.
Yeah, but your barrier is still generated at one loop. You just can make up of some certain amount of the barrier from the tree level term. Yeah, but still it's there from the.
Sorry, so you're saying there's parameter choices where that barrier, so there's gonna be some temperature range where there is a barrier and then that barrier disappears.
Yeah.
So you would have a fourth panel.
Yeah, that's right.
With even lower temperature,
Yeah.
with no barrier. But then you still have to know that transition occurs through bubbles and not just waits until the barrier disappears and then rolls.
Yeah, that's right. So our the inverse time scale of this transition is the beta parameter is typically very large. So it's
So this global
It's
flow
happening
has zero
very fast.
temperature definitely into the bottom right one.
Right.
So the adjustment of the lambda sigma 5 actually adjusts the height of the given temperature.
Yeah,
The
but
barrier
what I'm
between the-
saying is that you have two, right? It's doing some funny thing, right? Right, it's going, this one's going out and it's going up. And now you got a barrier between the two, and then you're saying that the barrier is going away.
Yeah, the barrier has two evaluation. One is at a finite temperature, lower the temperature, lower the barrier. So
Right.
yeah.
But if you want a first order transition, you need to have the transition happen quickly.
yeah.
So the barrier has to be, I suppose, small or thin or,
right.
uh,
Not too
so-
high.
because otherwise it'll just wait.
That's
That's
right. That's right.
And then
that's
you'll
right,
have the transition
Yeah.
happen anyway.
Yeah, so the height is adjusted by that part.
Yeah.
He chooses his beta parameter.
It's a few hundred, so it's fast enough.
Sorry to be stuck on the previous topic. Here is absolutely, it's an explicit breaking now, but it doesn't matter, but it's an explicit breaking, you can see it because, let's say sigma is assigned, the lepton charge 0. Then S carries
Well,
one.
you can make it explicit, but it doesn't.
No, wait. S carries charge 1, lepton number. Then there is a phi SS. You can choose phi to carry the charge 2.
Yeah.
Then it's in there. But there is phi sigma squared, which necessarily weighs.
Oh, 5 sigmas.
Yes, yeah. So there is an inconsistency. At the level of the coupling. So either mu, depending on how you assign it, either mu twiddle breaks the lepton number or some wise break lepton number. But so there is no matter. That's is actually a better answer than the spontaneous break, right? But it's not clear whether what you achieve with this, because it's not a spontaneous breaking, then why all the scales? Just to have the gravitational wave. That's your design choice to have life more interesting. No specific.
I see. Okay. Yeah, thank you.
So if it doesn't have mu to that term, right, then it's spontaneous.
If you erase mu theta,
Yeah.
will the spontaneous breaking if there is a breaking? And or then the neutrino stay massless, or you pick up a minor, right? You find the but it looks like an exclusive group. That's the answer. Proof thing. Ask theory.
I guess the problem why the new filter form is important. The new set is very small.
Oh, yeah, because we need to generate a small mass scale for the inverse seesaw.
The mu is actually not small. It's a design to choose that a value to cancel the rest of its potentials.
Oh, no, don't cancel.
No, you
It's a
have to
trilinear
make
term.
the value of phi small. That's all the rule.
Yeah, right.
Okay.
Right, but you don't need to cancel with anything.
No, you really cancel big number. So without the mu tilde term, what's the generic size of the phi value? Phi value is at square at mu phi over lambda.
Yeah, so even if without that term, your phi is still here, it's still zero. It doesn't go to a very large number, right? Because here is more deeper. So without this mu, you get zero. With a mu, you get a very small number.
No, I'm asking what's the value of phi value? And without mu tilde term, generically,
yeah, that's zero.
it is zero.
That's zero.
Oh, but so you didn't make a negative.
No.
So mu phi is not negative.
No, they're all positive.
Phi is
It's zero and the explicit
sorry.
gives you the bit of
no, sorry. The value. So here I'm doing field expansion on sigma, right? So sigma large means that I have negative mass term. That is negative
no,
sigma phi.
There's no expansion here. I evaluated this at the origin. So,
I'm talking about VAB, global
okay.
minimum.
Okay, if you want to expand.
So what's the VAB of phi without mu tilde?
Zero. Right? That's this one. Right? This one.
Near zero.
No, how can we be near zero? Look at your Lagrangian parameters. Okay. So
Yeah, right.
phi is non-zero. You have a negative mass term from the sigma phi term.
Yeah.
Okay. So large negative parameter, unless it cancels the mu squared term. Otherwise, the VAB is not.
No, it's positive. Okay, it says lambda phi with a phi to the 4 with a minus sign, and then sigma phi squared the same sign as phi to the 4. So it's a positive mass. So you see the quartic for the phi, that's a negative.
Yeah,
term,
okay.
right?
Yeah.
And the second quartic that is phi squared times sigma squared also has the same sign. So therefore,
I see. So it's
really
positive.
as written it as a zero web, and then explicit breaking gives it a small shift. Explicit breaking of the
Oh no, sorry. Then that is incompatible with the sign of mu phi term and lambda term. Okay. So they are opposite sign.
Yeah, they're opposite sign, which means it is negative mass to it.
Yeah, so it has a VAB. The
So that's
VAB,
a bit.
yeah, the VAB is mu phi.
Do you make here?
Yeah.
Yeah.
Yeah, but here is not as negative as here, so
Yeah.
your true value still goes to here.
But
You're
your
correct.
overall
But you're
mass,
correct. It's-
your overall mass is going to be a combination of lambda sigma phi times sigma squared and mu phi squared.
Yes, so if they are exactly cancelled,
Whoever wins.
if the second term is larger, then it's zero, right?
Yeah.
If the second term is smaller, the size is mu phi squared. Okay, the mu phi over.
What's the second term? You mentioned.
The value of phi is mu phi squared minus lambda sigma phi sigma
okay.
phi
Yeah.
squared. Okay, so
Okay.
you need that term to be negative.
There
Yeah,
should also
yeah.
be, I guess, a lambda h to the 4th.
Yeah.
So it's,
Yeah.
Oh, yeah, sure. For the case, I
it's
just,
just doing the sigma phi.
yeah.
Okay.
Yeah, we can talk about this. Yeah. Yeah, okay. Yeah, the phase space. Yeah,
Well, next slide.
Sorry, one second. No, the sigma gets a big then, right?
yeah, right. Yeah.
Is lambda sigma h really small?
Yeah. And yeah.
Oh, it's because otherwise that would give a big mass.
Yeah, that's right. That's right. Yeah, yeah, yeah.
Negative. But
Okay, so yeah, we see that this gives you the portion in first order, second order, and there's a very thin, this orange band gives you a very strong gravitational wave for the cycle to be observable. And here, in this plot also shows the alpha beta parameter for different fixed numbers of lambda sigma along this other line. You vary this lambda sigma. So from this, you basically see that for lambda phi and lambda sigma, you typically have a large parameter space that can give you the desired two-step and first order phase transition. But you need to choose this lambda sigma phi very carefully to make your gravitational wave strong. Okay. So with this knowledge, we choose some benchmark parameters for the values mentioned and the gauge coupling to 2023, and these scalar coupling are all around from -3 to only 1, while mixing the Higgs and also some reasonable transition come. So yeah, and with this parameter, we apply the previous techniques I mentioned, and here shows the gravitational wave. So as you can see, we're very careful about our results. So this solid line is our major result, and with the two loop accuracy, this gauge independent treatment, and these dashed curves are the two loop result without the gauge independent treatment, and this dotted line is a one loop result, and this band shows you the variation of the scale dependence.
How using the dimension over that dimension?
Yeah, that's right. Yeah. So that's for the gravitational wave signal. I'll get back to this later, but now let's have a look at the Kleider signal. So
that method that he's using, I think it's natural here because your n squared phi's are much below t, which is TV, like those phase terms.
Yeah. That's right.
In the phi length, that's one. That's a hierarchy.
Yeah, he's got a big hierarchy between n squared phi.
Yeah. That's right.
So that's why it's natural for you to do this dimensional.
Yeah. That's right. Yeah. So now we translate this parameter into the mass with the heavy neutral lepton and mixing into neutrinos, and so all these numbers are well below the reach of LHC, but on the Muir Kleider, you can single produce it from this diagram, and here shows the cross-section versus the center mass energy of the Muir Kleider. So you typically expect around 30 units for these benchmark parameters, which is at the borderline of being observable. And we also want to have a look at these heavy scalars. So here shows the mass of the sigma and phi, and also this mixing with the sigma and the Higgs. So you can either single produce a Muir Kleider from gauge boson fusion, vector boson fusion, or on a hadron Kleider from gluon fusion. And here shows the cross-section normalized by the mixing square. So you see that this 100 to the SCC and 10 to the Muir Kleider typically give you a strong signal, and you will expect for benchmark 3 and then 2000 units at FCC and the 20 units at Muir Kleider. So as I said, we want to talk about some complementarity, and as we already seen, our benchmark have very rich phenomena and very rich physics. So the first plot shows the effective mass of the neutrino with no beta decay versus the minimum of the neutrino mass. The second plot is the Muir Kleider signal, and the third plot is the gravitational wave. So next, we would like to do a simple scan to see how changing this parameter would change this picture. So
Left part, I will never reach your maximum.
left.
Yeah. There's no experiment temperature.
It seems so. Okay, for a very small true mass, and yeah, okay. Yeah, but there are that you can reach. Here we do a scan that on this tablet of sigma and the web of the scalars. So, and we found an interesting result that for this neutrino with no beta decay and the Muir Kleider are only sensitive to this product of this Mikala and the web, which give you the mass scale of the highly neutral lepton. However, for this gravitational wave, the gravitational wave spectrum have very different dependence on these two parameters, which would potentially allow us to separate out the contribution from these two parameters. So from the simple scan, we can already see that the gravitational wave spectrum would give us some complementarity to the collider search. So next, we would also like to do a full scanning of the parameters. So here is our strategy to do the scanning. So we fixed to.
Maybe you can show us a direct result. We don't have this room for too long. 7 minutes, not more time.
Yeah, this is our last two
Yeah,
slides.
go with that.
Yeah, the last two slides. So we fixed the math of the initial lepton and the sigma and gauge coupling to scan the rest of the scalar coupling, and here shows the result. So here shows all the scalar parameters that can give you a strong and observable gravitational wave for this side. So basically, we see that there are only some slices of the parameters that can give you a strong gravitational wave, and this means that the gravitational wave observation can put a very strong constraint on your parameter space. So that's my last figure, and let me conclude. So in the first part, we learned that there's some subtlety in the calculation. So we use dimensional reduction and consistent expansion to cancel all these unnatural scale dependence and gauge dependence. And in the seesaw model plus the two scalar, we see very rich phenomena. We have neutrino mass, we have strong gravitational wave, we have collider signal. And we also learned that the gravitational observation is highly complementary to collider searches, so it can help us to greatly narrow down the parameter spaces and probe a lot of parameter space beyond the collider. Okay, so that's all. Yeah, thank you.
Any urgent question?
Yeah, is there, what is the other motivation for the inverse seesaw beyond this particular model?
Oh, so another reason is that the inverse seesaw can be observed in some the heavy neutral lepton in the inverse seesaw model, and potentially see in several future colliders around TV scale, and the gravitational wave spectrum that is disaggregate sensitive
Not
to.
gravitational, it's because I want to generate, the whole point is to get the neutrino mass.
Yeah.
So is there other motivation for the inverse seesaw over the normal seesaw method?
Oh, over the normal one, because it's doubly suppressed.
To see them at colliders, to access the right-handed neutrino.
To have a direct.
Because the normal seesaw scale is too high.
Yeah.
It's inaccessible. So,
Yeah.
I mean, it could still be a TeV, right? It's still, so.
yeah, it's when you directly write down a small, very small impala.
Right.
So that's kind of undo the.
Yeah.
When we use seesaw to explain small is the neutrino without the small impala. So this break the problem into two parts.
Yeah, you're right, you can have small Yukawas and the particles, Yukawas 10⁻⁹, and then you know the G scale.
Right.
But those if that's the only interaction, you can't produce that, right?
Right.
So you delegate your small mass to this new parameter, which you choose to be small, but it's irrelevant on the scale of the colliders because now you cover it. More
We want to see.
more discoverable more.
Yeah, we want to see
Yeah,
all
yeah.
that,
random.
Yeah, so in our model, we actually try to not tune too much. All our recoveries are very reasonable. So that's a good side.
But then you also have a limit based on this N effective from omega gravity line, right? Because you have phase transition.
Yeah, you mean on the like the degree of freedom?
I thought there's a limit coming. N effective.
Yeah, on omega.
On omega gravity rate, but I think that's a limit on your beta.
Like a theoretical limit or some observational?
Because that controls the.
Yeah.
strength of the phase
Yeah,
of
so
the time.
actually our beta are not designed are not supposed to give you too strong version because they are all around a few hundred. So
Your beta is around a few.
yeah, it's a few hundred. So it's
Yeah, we've had a lot of very exciting discussion. Let me remind you, he will be here and Clint will be here for the whole week. We can just partner them and discuss more physics with them. So tonight we'll have a dinner arranged with Arthur. Pei Yang will help organize it. So if you want to join, just Pei Yang will ask about that. Okay. Okay. Thanks everyone.
Yeah, okay. Yeah, thank you for all the questions.
Yeah. So you calculate the finite computer potential by hand, right? Not by program. There's no.
Yeah, there is a program, but I also calculate by hand.
What the program do the dimensional reduction for you?
It does everything actually. Yeah, but I do calculate the total. Oh, called DR algorithm was released in 2022.
DR
dimensional
reduction.
The algorithm DR algo.
Yeah,
yeah. It's you can implement all the new models like they have like SU5 they have 2x W model, you know.
So naively in the beginning your job is to scan the fragments, right?
Yeah.
So what did you improve on?